afternoon. Hopefully you guys are having a great afternoon and hopefully you had a good weekend as well. Before we begin, I want you to watch this video if you haven't already. At that point, you guys can fill in these 4 rules. So if you need to pause, do that now. Welcome back. Where we want to first go off is actually on the electric field diagrams, the problems. I want to take a look at that first, and then we'll get back to some of the notes. So this is found on page 4 of your problems. We want to take a look at different charges here and how they interact within the field. And so what we have in front of us are a variety of different options here, with only a couple of them being how they actually should be. This first one right over here, this is after watching the video, you would have seen that with a positive source charge, and this is what we're looking at here, there are going to be field lines that are going to be radiating out of it. And for the negative charge source, it's going to be towards. And that's why these two here are the correct ones. This one over here is not correct just because you should have an even distribution. So there shouldn't be more field lines coming from the source charge on the right side compared to the left. There should be the same number in both. Clearly, number 2, there's an intersection here where lines should not be overlapping. You guys can attempt some of these on your own at your own leisure there, and we'll just move on to something a little bit further on here, I believe. Right over here. So hopefully you guys will have a chance to try to draw your own. What we have in front of us is a positive charge and a negative charge. And what are the interactions happening? Well, remember, with positive charges, you're always coming from the charge and the field lines are drawing outwards. And for the negative charge, the field lines are drawing towards the negative charge. A couple things here. I try my best to make sure that there's an equal representation of the lines because there's a similar charge. This is positive one, this is negative one. So they have the same magnitude, but they have obviously a different sign there. So the magnitude, or aka the number of field lines, is going to be the same for both of them, but the direction obviously is different. So it's moving out, radially out from the positive charge into the negative charge. When we look at the second option right over here, option B, or question B, here we have a negative charge that is twice the magnitude of charge over here. And so what you see is that there's going to be twice as many field lines towards the negative charge. And clearly, as we're going through this, some of the things that may have been mentioned already is that positives are going to be moving towards the negative side over here. Later on, I guess we have some values where we have some negatives over here and here. If we brought the negatives closer together, there is going to be some repelling going on where these lines, if I kept drawing this negative line over here, it would be kind of going this direction like this. So it's going to be not moving anywhere near this other negative charge over there. I hope you take a moment to click on the link and give this electric field hockey a try. I want you to create a situation in which you are adding multiple forces to score a goal. And so you're going to have to kind of play around with it. You saw probably at the beginning of the video too that I created something in which it was very elaborate. Obviously, you could kind of go about something very, very simple. We know that if you have a negative and a positive, the positive charge is going to be attracted to the negative force here. So we could have just like one negative charge right over here. And yes, look at that. It's very, very simple. So instead of making it that simple, I wanted to challenge you guys to have multiple charges, so a minimum of 2 or more, and then attempting to score on the goal from that. Hopefully you had fun creating a situation in which you were able to score a goal using the test charge. At this point, I want you to go to your notes, and you'll be on page 6 of your notes. And so we're looking at equating electric fields here. The big thing to keep in mind here is that an electric field is in fact a vector, so it needs a direction when you are giving an answer or making calculations. You're going to need to know, well, in what direction is the electric field facing and going towards. So we've already looked at a positive source, and we know it's going to be traveling radially outward from the center, and with a negative source, all the vectors and the force or the field lines, sorry, are going to be directed inwards. The other two parts to this formula right over here, if you look at this, the electric field is equal to the electric force felt by a charge, and we call that often like a test charge. It's often something that's really, really small, and that way it doesn't have much of an effect on the overall field, because technically it does. Just like you and I have an overall effect on the gravitational forces, but it's just so incredibly small that it's just not going to ever account for anything. So over here, electric field is the force felt by the charge over whatever the charge is. Another way to write that is the force is equal to the charge multiplied by the electric field. Thing to notice over here, the units for the electric field is in newtons per coulomb. So that is going to be as reduced as it is. There's no fancy new term for what that looks like. It's just newtons per coulomb. So the last thing to mention before we get into the questions here is that when we're looking at the electric field here and making these calculations, we're always basing it on a positive test charge. So if the field, for example, was going east and the charge was positive, then the force on that charge would also be east. If the electric field was, say, going north, and again, the test charge was positive, then the force also would be north in addition to that. So just be aware that if you did have a negative charge, it would then be in the opposite direction. So if the field was, say, going east, and you had a negative charge, say like an electron or multiple electrons, then the force here would be going in the opposite direction. It would be going to the west. So just be aware of that. You'll see later on that I even kind of drew some pictures out just visually, just to get a better understanding of what that looks like in each situation. So for the first example here, we have a force with about 400 coulombs, test charge in an electric field with a strength of 800 Newton coulombs going towards the west. And we're saying, well, what is the force? So a lot of coulombs right over there, but it ends up being relatively simple. So again, you can kind of choose which one of these. They're the same formula, they're just rearranged a little bit. So all you're doing is plugging in values. And as you notice on the final answer here, there's 4 significant figures, just like there's 4 sig figs with each of these values there. And also bear in mind that there's a direction for the force as it's a vector, of course. For this next example here, an electric field with a strength of 4.8 times 10 to the 18 Newton coulombs. It's facing south. So this is our electric field right here. A charged object feels a force of 12 newtons south, and so that is our electric force right over here. And now we're looking to say, well, what is the magnitude of the charge on that object? Just rearrange this formula, plug in your values, and you get a value for Q. Just bear in mind that often when you're punching this in on your calculator, scientific notation, make sure that you either have the brackets over here on either side, or you punch this in first and then go 12 divided by that value. Couple things to note on your formula sheet, you will have exactly what one charge is, like 1 electron in coulombs, I believe. It's 1.6 times 10 to the negative 19 coulombs. Something on your formula sheet that I would like you to change though is that 1 coulomb is actually 6.24 times 10 to the 18 electrons if rounded to the nearest hundredth. The way that 6.25 was written down there is by just taking the inverse of this value here. So because this value is rounded by a little bit, it ended up having a value off by 1/100th. So not a big deal, but on your cheat sheet, you can change the 6.25 to 6.24 times 10 to the 18 electrons in every coulomb. So there's a lot of electrons in every single coulomb. And so in this question here, it says, well, how many electrons has it either lost or gained? And so if you're looking at a charge of 2.5 times 10 to the negative 18 coulombs, and keep in mind this is a positive charge, and the question you could ask yourself is why? Well, up above here you have a field strength that's to the south, you have a force that's to the south, and therefore if they're both facing the same direction there, then that means that you have a positive charge because they're both in the same direction. So that being said, if you have a positive charge, that means that you're going to have to lose electrons in order for it to have an overall net positive charge. At this point here, all I'm doing is I'm just doing some cancellations. If I have coulombs on the top, I have coulombs on the bottom, and I then go ahead and multiply. My coulombs will cancel, leaving me with just electrons. And so I just chose to use the one that says that 1 coulomb is 6.24 times 10 to the 18 electrons. This one right over here, this should really be 16 electrons if you're rounding this up to the nearest electron. Obviously, you can have 0.6 electrons, but again, this is just a question here. Let's move on. All right, here we have our last page before I'm going to send you on your way to actually attempt some of these questions on your own. A very strong electric field is supporting an object of mass 10 kilograms against Earth's gravity. The object is missing 1 times 10 to the 30 electrons. So if it's missing electrons, we know that we have a positive charge here. What is the strength of the field? So there's always a variety of ways in which we can go about looking through this. The first thing is this, is that there's a very strong electric field supporting an object. So we're going to look a little bit more at this when we talk about Milken's experiment, in which he basically allowed certain charged particles to just kind of float around. That's kind of what's happening here, is that there's an electric field that is going to be opposing the force of gravity. So it's going to be equal and opposite if you're going to have an object that's just being supported. And so that's what we really have here. We have a force net, which is force gravity equal to our electric field force. And so what I did then was just break each of these things up. Force gravity is also just mass times gravity. And our electric force here is just our charge, our test charge multiplied by the electric field. And then we take a look and say, well, what are we looking for? We're looking to determine what the strength of the field is. So we just rearrange this equation for our electric field to be equal to mass times gravity, and all I did was divide by our test charge on either side of the equation here. At that point, you just plug in your values, which are given. The one that is not given, though, is our charge. So we take a look here, it's like, oh, we don't actually have our charge. We know how many electrons there are, but we don't know what the charge is. So just bear that in mind. These at some point might even be committed to memory. If not, you can always continue to look at your formula sheet. So the first step after kind of getting to this point right over here is recognizing, okay, we have mass, we have gravity, we need our charge. So then I went over here and I said, well, charge is right over here. We have a certain number of electrons. To get rid of electrons, I put that on the bottom of this fraction. And I say, well, what is 1 coulomb equal to? It's equal to this right over here. And so once the electrons cancel their units, we're going to be left with coulombs. So it's basically this value divided by 6.24 times 10 to the 18. So the amount of charge we get is 1.6 times 10 to 11. And remember, it is a positive charge because we were missing electrons over here. So now you can bring this value into the equation and get an answer there. And because I said before, why is it going up, this electric field? Well, we said before that the force is going to be in the same direction as the field when you have a positive charge. We have a positive charge, and we know that our force has to be upwards because it's going to be equal and opposite to our electric force. And so that's why we have our electric field over here. The direction is up. Okay, here's your final question. We have an electron with a mass of 9.11 times 10 to the negative 31 kilograms. This value can also be found on your cheat sheet. This electron starts at rest in an electric field with a strength of 3.0 times 10 to the power 3 Newton coulombs. Now I forgot to include a direction, so just include east. And if we go over here, we might even be able to just kind of write that in right over here. So I'm using Cami over here, and hopefully you're going to be able to get that to work later on with one of your assignments. So electric field of the strength of this value to the east. We're asking, what is the velocity of the electron after 3 seconds? So there's a lot of pieces to this puzzle, and so the first thing is to just define just a couple things. So first of all, our charge right over here is going to have a negative value because we are looking at an electron. So keep in mind that whatever direction the electric field is facing, the force is going to be in the opposite direction to that. So if I did tell you that this field right here is pointing towards the east, that means that our field is going to be pointing towards the west. And again, that's because it's an electron, we have a negative charge. Normally we're dealing, when you're looking at the same direction, it's going to be a positive charge object. So just bear that in mind. Positives and negatives make a big difference. First thing we can do, actually, if we are looking at finding velocity, obviously one way we could go about doing that is to do our TAD-VV. We don't have time. We could figure out acceleration based on the formula force. Net force is equal to mass times acceleration, and we do have the mass. So if we're able to find acceleration, well, we can find acceleration from force. So if we can find the force, we can find the acceleration. If we continue with TAD-VV, well, we do not know our displacement. We do know what our initial velocity is. Our initial velocity is 0 because the object was first at rest. And it also gives us our time actually right over here. So we have our time, we can figure out our acceleration, and we have our initial velocity. So with those three pieces of information, we can find out what the final velocity of this electron is after 3 seconds. So it's about kind of knowing where you need to go and then how do you get there. So let's start from the beginning here. We're going to be looking at, well, what's our force equal to? We look at that, it's our test charge, multiply our electric field, and we get a value right over here. Something also that I should add into this right over here is the following. We should be adding a negative sign here, because if it's negative this times that, we're going to get a negative value over here. So what this is really saying is this, is that we're going negative 4.8 times 10 to the negative 16 newtons to the east. Or what you could write down, and again, bear my writing here, I'm writing with without a mouse, this is just 2 fingers on my trackpad here. You could go with a positive value of this whole thing, that 4.8. So just imagine that I wrote that whole thing out, and then it's going to be to the west. And again, that's a horrible W, maybe do that. So that's what it looks like, negative 4.8 to the east, or a positive 4.8 times 10 to the negative 16 newtons to the west. And so like I originally said, because it's an electron, it has a negative charge, if the field is facing to the east, our force is to the west. Once we found our force, well, now, like we said, we can find our acceleration. So we can go over here and we say, what's our total forces? Well, it's just our electric force right over here, which is mass times acceleration. Rearrange it and then plug in our values here. Once we get a value for acceleration, I already mentioned that we had initial velocity, acceleration, and time. And so what you would just need to do is just find the right formula in the kinematics equations. At that point, you can just plug in your values and get a final answer here. And there's also one thing missing in this final answer, and that's just due to the fact that I had forgot to include a direction over here. So with our acceleration, there should be a direction there too. And so that direction for for acceleration is also going to be to the west. And down below over here too, if we're talking about where's our final velocity, well, if it's accelerating to the west, if the force was to the west, then same with our final velocity there. So that concludes the notes here. I would love for you to guys to give a couple of these a try. So I want you to skip this page for now, and the questions I want you to try for this lesson are on page 8 and 9 on the problems booklet. So it's equating electric fields, and so you have your questions over here, and you also have the answer key already, but I want you to give those guys a try. So good luck.